Greetings, folks. It's Professor Fiore, and welcome to part 3 of our discussion on room acoustics. In this section, we are going to talk about room resonant modes, things that are caused basically by standing waves. Now, in a prior video, we were talking about what happens in a room. So just imagine this big square over here is a room with the sound sort of bouncing around on all the walls, like a pool ball, a billiard ball bouncing around on a table. That works well at middle and high frequencies. When we get to really low frequencies, we have to sort of change gears and we look at this idea of room resonant modes. You'll hear things like eigenmode or eigentone. Basically, we have standing waves built up in the room. This sort of break between the two is defined by something called the Schroeder frequency. And in typical sorts of rooms that you'd be in, your home, school, business, that's probably somewhere in the range of 150 to 200 hertz. So above that, we can use that sort of ray tracing approach we looked at in the prior video. At lower frequencies, though, we're going to have to look at this system that's sort of dominated, if you will, by room resonant modes. Now, ignore the equation in the upper left-hand corner for just a sec. And I want to say a few things at the outset. One of the things you're going to see here is that probably the worst shape for a room, because people are always asking about this, what's the optimal shape for a room? What's the appropriate dimensions? The worst thing you can do is make a room that's a cube. Height, width, and depth are the same dimension. That's the worst thing you can do. The second worst thing that you can do is make something so that these dimensions are integer multiples of each other, right? So a bad room would be one that's 4 meters by 4 meters by 4 meters. An almost as bad room would be one where it's maybe, let's say, an 8-foot ceiling, a 16-foot width, and a 32-foot depth, right? So now you got factor of 2 and a factor of 2, right? Or a factor of 2 and a factor of 4, however you want to look at that. That's almost as bad. Another thing that's not so good is if you have a high aspect room. In other words, like a long, narrow room. Okay? So just to kind of give you an example, right? I'm going to use this big space over here. I'm going to pretend that this is sort of an apartment that a friend of mine used to live in years ago. When you walked in, all right, so here was a door. You were greeted with this really long, skinny hall. This was hardwood floor, just hard drywall plaster for the walls and the ceiling. And at the far end, there was a door that you would go into the remainder of the apartment. So here's what would happen. When you would walk in, if you had, like, let's say, clapped your hands or, shouted or something, the sound would go all the way down here, hit this highly reflective back wall, which was maybe 15 or 20 feet away, and then come all the way down here, hit this wall, very little loss, and then repeat itself, just like we were talking about with the billiard balls before, right? And this would just go on and on and on and on, just bouncing back and forth, losing very little energy every single time. So with that kind of distance, you were looking at maybe a 30, 40 millisecond round trip on here. And the end result was this sort of trail of very tightly spaced, sort of overlapping echoes. And what you would hear was a very robotic, sort of whiny sound that would be trailing after all the sounds you would make. So if you clapped your hands, you would hear clap as it would fade away. Right? It was really kind of strange. So that's that's an equally bad thing, let's say. Okay. We absolutely do not want to do that. All right, so let's continue with our idea of the room resonant modes. We've got this idea that it's really dominating at the lower frequency end. Okay? All right. If you look at one dimension on here, All right, one length. You can think of this as setting up kind of like we did with tuned pipes, right? You can set up a resonance in here. And essentially what ends up happening is, think of like a vibrating string, right? What ends up happening is on the walls, right, on the opposite walls, we have the highest pressure. What ends up happening is you'll get sort of a trace like, ooh, that's really terrible. I don't like that at all. Let's try that again. So we'll get this sort of, that's a little better, kind of a thing. So just imagine this is like a string vibrating. So it's going, back and forth like this, right? And of course this would be symmetrical. This is essentially half a wavelength. So right here would be a positive peak, down here is a negative peak, but it's flipping, 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 okay? So out here is the high intensity. I'll just put a bunch of pluses over here. And the same thing on this wall. All right, this is all the high intensity stuff. I'll relate that back as saying a high SPL, okay? And then right in the middle here, this is the low. And this is all the way across the room, right? All the way across this, perpendicular to the axis here that I'm drawing. So we've got high, low, and high. Now the low, that's referred to as a node, just like on a guitar string. The nodes on a guitar string, vibrating guitar string, would be at the bridge and at the nut, or a fret, right, if you were fretting it. So that's where you get really no motion, right? No motion. It's in the middle of the guitar string that you get all the motion. Well, that's sort of the inverse of what we see here. That is called the antinode, or antinodes in this case. All right, so you have an antinode over here, and we have an antinode over on this wall as well. Okay? Now, this occurs not just on that one direction, right? So that was going this way. That also occurs on the two other parallel walls, like this. And it also occurs on, sort of where we are, let's say orthogonal to this plane that you're looking at right now. In other words, coming at you and away from you. If these are the four walls, I mean the floor and the ceiling, right? Which I can't really draw here. I'll just sort of like draw a circle here to represent that. So we've got three pairs, okay? Now those modes are referred to as axial modes, all right? And the lowest frequency in here is occurring at essentially 1/2 wavelength, right? The blue diagram here is showing that the blue graph is showing 1/2 of a cycle, so it's 1/2 wavelength. Now remember your wavelength, right, lambda, your wavelength over here, is going to equal the velocity of sound, so you can do this in feet per second or meters per second, divided by the frequency. Now, if I was going to do this in customary US units, velocity, room temperature, maybe 1125 feet per second. If I was looking at, fairly low frequency, 100 hertz, let's say, an easy number, then we're looking at a wavelength of, 11¼ feet. If we're going to do this in metric, velocity 343 meters per second, again for 100 hertz, looking at 3.43 for the wavelength. All right, now you have to come out and double that, because I'm really only talking about half a wavelength, okay, as far as the frequency is concerned. So I would simply solve this the other way around. In other words, the wavelength is the dimension, right? So if I would say I have a dimension over here that's 10 feet, okay, I know what the velocity is, and I would simply solve to find what the frequency is. And you discover very quickly these, for normal rooms, you get a lot of frequencies at, 100 hertz, 50 hertz, 30 hertz, 65 hertz, things like this, right? So, like I said, the lower end of the spectrum, right? Below the transition with the Schroeder frequency. Okay, now this is where it gets a little bit more fun. Not only do we get that, but we get, as you might expect, integer multiples of that. So if one of those resonant frequencies happened to work out to 50 hertz, which would be typical, like in a classroom, you're also going to get the same pattern occurring at 100 hertz and 150 hertz and so on and so forth. Okay, you're going to see 200 hertz and 400 hertz and all of these nice multiples. So what would end up happening is you could imagine fitting in here not just not just the half wavelength, right? Like, so you would end up with something that kind of goes like this, right? So you've got node, 3 antinodes. So there's a peak amplitude here in the middle of the room, along with these two sidewalls, all right? And this is three-dimensional, right? You have 3 axes, so this happens simultaneously. You can excite these resonant modes with some kind of frequency source, right? Some kind of signal source. And what this means in practice is if you're standing here in an antinode, right, against the wall, or in this particular case, right in the center, you get an exaggerated sense of that frequency. And if you're standing at a node, it sort of disappears. Okay? Now, continuing. Not only do we have axial modes, we have tangential modes. So the axial modes basically involve 2 surfaces, right? 2 opposing walls, parallel surfaces, floor and ceiling, side walls, right? Front and back walls. The tangential modes involve 4. So you could imagine, you can visualize this. It doesn't really do this like ray trace thing, but you can imagine something like this. Right, it's 4 surfaces. So it could be bouncing on the 4 walls like this. It could be going from the front wall to the ceiling to the back wall to the floor back to the front wall. Or you could be looking at the floor and the ceiling and the 2 side walls, right? 4 surfaces. The intensities for the tangential modes are not as strong as they are for the axial modes. In other words, to get the same SPL change, you're going to need more power, more energy input for a tangential mode than you would for an axial mode. And then finally, we have oblique modes. And as you might guess, the oblique modes, all 6 surfaces, right? I'm not going to talk about rooms that are, some weird shape. All right, this is just, 99% of the rooms you're going to walk in are going to be some kind of, rectangular structure. All right, so this involves all 6 surfaces, and again, there's sort of a reduction in the power compared to the tangential, just as the tangential was compared to the axial. All right, so out of the system, the axial modes tend to be the dominant modes. And now we can talk about this equation up here. C is the velocity of sound, right? So you're either going to do the, maybe 1125 feet per second, or you're going to do the 343 meters per second. And then over here, D, W, and H are the depth, the width, and the height of, the particular room, the dimensions. P, Q, and R are essentially mode numbers. So if you throw a 0 in there, you're not going to get that particular piece. In other words, if I was looking at an axial mode, right, and I want to see what it is for the depth, I would put a 1 in for P and a 0 in for Q and R. So what ends up happening is you get 1 over whatever that distance is, right, that depth distance, feet, meters. They're squared, but these other 2 terms are going to turn into zeros. You take the square root of the square, you end up with the same thing. In other words, you end up with 1 over the distance times C over 2, right? Over 2 because it's half a wavelength. That's your base. That's where you start from. And then you work up from there, right? So you throw in a value in here, like I said, maybe 10 feet, okay? And I'm looking at the first one, the fundamental, the blue one that I drew over here initially. So that's going to be 1 over 10 feet. You square that, you take the square root, so it's still going to be 1 over 10. It's still going to be 0.1, right? And then C over 2, so you have your 1,125 feet, right? So you divide that by 2, and you get about 560-ish, and then you multiply that by the 0.1, and you're looking at 56 hertz. So if this wall is 10 feet, right? I'll go this way this time. So if this wall is 10 feet, then you're looking at about a 56 hertz resonant mode, all right? And what you would see in that case is the high pressure would be along here. In other words, the antinode. The high pressure would be along here, the other antinode. And then right in the middle, we would have the node where it would be minimal SPL, all right? Then if I want to look at the sort of, I'll call it the harmonic, right? The octave, you would put a 2 in here, or a 3, or a 4, or a 5, and you would continue in this fashion. Now, when you want to look at the tangential modes, you would be looking at 2 of these. Maybe the depth and the width, or the depth and the height, or the width and the height. The odd one out, you put a 0 in for P, Q, or R. Right? So if you want to find the fundamental for the depth and the width, you would put a 1 in here for P, and a 1 in here for Q, and a 0 for R. If you want to find the fundamental for the width and the height, 1, 1, 0, right? And, like I said, you put in the appropriate distances for the width and the height or the depth or, whatever it is that you're looking for, and you grind that thing out and you come up with the appropriate frequency. Now, what you're going to discover is if you start doing this, these are going to sort of gather up very quickly. In other words, the very first few that you calculate with the axial, they're kind of spread apart. But then the gaps start getting filled in with these higher order things. And yes, on the oblique version, you're going to put a number in for P, Q, and R. There are going to be no zeros in here, right? And you'll figure out what the oblique modes are. So like I said, pretty soon these things are very, very close. They kind of overlap. And this nice sort of division of hot spots and cold spots, so to speak, as far as SPL, that kind of disappears. And, that ray tracing version we were talking about before is really what starts to dominate. All right. Okay, so let's clean this up a little bit. It's getting kind of busy. How, like in a recording studio, how do you deal with this? Because this could be kind of a mess. I mean, there are preferred dimensions that you can use, but one thing you can do is make a room that's not a rectangle. Right? You can slope the ceiling. You can splay the walls. So, a simple kind of thing that you could do, and I'll see how well I can draw this. Let me change my color over here to gray. You could build, a rectangular room and then just sort of splay the wall a little bit so it kind of goes like this. And then you could splay this other wall, right? You could splay it on either dimension, but I'll just do it like this. So what ends up happening is this wall is not parallel to this wall is not parallel to this wall down here, and you don't have as big an issue. Now, there will still be standing waves in the room, but it's not going to be this nice regular sort of pattern that you get with, a nice rectangular room, all right? And hopefully now you can see why a cube is so bad, because each of the dimensions, you're going to get the same exact pattern at the same exact frequencies. Everything piles up, okay? Not so good. One cool thing you can do for, let's say, like a recording studio would be to splay the walls kind of like, let's see, what's a good way to do it? I'll put it in here like this. You can do something like this. Oh, that should be symmetrical. But you basically make like a 5-sided room, all right? So you could have your monitors out here, mixing desk here, and you're sitting out here. This can work pretty nice, right? This could be a fairly nice sort of situation. All right, it's beyond, let's be honest, it's beyond the budget probably of most people to build, let's say, a listening room like that. You're going to be pretty well constrained to some kind of rectangle. But like I said, there are certainly things you can't avoid there. All right. All right, so if you're thinking, boy, this could be kind of ugly, doing these calculations and so forth. Is there maybe a calculator I can use instead of trying to do this manually for all these different values, all these different PQR values to get the sets of frequencies? And the answer is yeah, of course there is. All right. There are some nice online calculators that you can use. Okay, here is one of them. This is a very nice calculator. I've got the URL for it right down here. This will calculate your room modes, your eigenmodes. And what I've done here is I've grabbed two of these and sort of stuck them together so that you can see what's going on. Over here on the right, what you do is, or this is split in half, right? So over here on the right, you put in the dimensions for your room. So in this case, it's 5.2 meters long, it's 4 meters wide, it's 2.4 meters high. All right, you plug those things in, and then it'll give you a graph. And you can see up here, this is color-coded, the axial modes, which are a little bit taller, they're going to dominate. The tangential modes are in sort of a dark blue, and then in a lighter blue are the oblique modes, right? So remember, that's 2 surfaces, 4 surfaces, 6 surfaces. And, when you get up high enough, up here in like this 250 hertz range, 150, 200, that area, this all starts to blur together. And it kind of graphs what's going on here. I wish this graph was just a little bit bigger, but it's sufficient. And then it shows you all the individual frequencies that would have been calculated using the formula. So for example, when it says 1, 0, 0, right? So the x direction over here, yes, y and z, no. So it's 1, 0, 0. So this is the fundamental for an axial mode. Here's the other axial mode, the second axial mode. And then the third axial mode is right here, right? 0, 0, 1. And then we start looking at the tangential modes where there's 2 digits and only 1 0, right? So here's the first one, 1, 1, 0. And then you've got another one over here, 2, 1, 0, and so on and so forth. And finally, we got far enough up, you're going to see, there's no zeros. So here's 1, 1, 1. This would be the fundamental oblique mode, right? So you just have a set of radio buttons. You click on which one you want to see, right? And it'll draw this really cool little box. So this is something that, I'm not going to try to draw with my, my little tablet over here. But basically where it's dark, that's the high sound pressure areas. So in this case, this is 66 hertz. This is an axial mode, right? 2, so it's the second one. And what you're seeing over here is, here's this wall. It's dark, high pressure. Here's this wall, which is high pressure. And then right in the middle, there's high pressure, right? So it's antinode, 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 and then the 2 sort of whitish kind of stripes. Those would be the nodes, which would be the low SPL, all right? Over here, by comparison, same room, right? We just happen to click on the 111. This is the fundamental oblique mode, right? And you can see that it's the corners, right? These corners are really hot. They have the dark shading on them. So that's where the SPLs are really high. Now, you'll sometimes hear people say, oh, if you want good bass, put your loudspeakers in the corner of the room, a trihedral corner. In other words, someplace like this, where 3 surfaces meet. And, what'll end up happening is you'll excite some of these modes, because here you're going to excite oblique modes. You're also going to excite tangential modes and axial modes. So yeah, you can get a lot of bass, but it's going to be very spotty, right? There's going to be areas in the room where the bass is exaggerated and areas where it's not, okay? Where it's, insufficient. Now, there's a nice experiment you can do, and we would do this a lot in our Science of Sound class. We would go into the lab, which is basically all cinder block and concrete. It's a decent-sized room. And we'd get a nice powerful subwoofer and a sine wave generator, and we would sweep around at low frequencies. 80 hertz, 70 hertz, 60 hertz, 50 hertz, 40 hertz. And trust me, in a room of that size, you'll get a lot of these in those frequency ranges. So you'll excite one of them. And what we would do is just walk around the room and listen, right, at a single tone. So you might have like a 55 hertz sine wave banging through this room. Average SPL, we might set that up to, 80, 85 dB SPL. And we'd sort of just walk around and listen. And you would walk into areas and you'd say, wow, it's really loud right here. And then you'd walk a few feet away, a meter or two away, and boom, it would just drop right off because you'd be walking from, an antinode to a node or a node to an antinode. And the other thing you could do would be to move vertically. People don't think of doing this generally. They just sort of mill around the room. But I would always say, crouch down, get down toward the floor, climb up on a chair in that same node. You can see if you get something like this, all right? Get out the SPL meter and see what you get. And it's no big deal. It was never a big deal for us to find two spots in that room at some particular frequency where there might be a 20 dB SPL difference. In one spot, you might be measuring, 92 dB SPL, and, a meter and a half away, it's, sitting there at like 70 or something. Really, really quite dramatic. It's not something that you're used to, in a home situation because you're listening to music. You're not listening to pure sine waves. Something that you can, really sort of zero in on that's going to specifically and sustainably excite these room modes, right? In music, notes come and go. So you might not notice that, all right? But this is something you have to be aware of. So, what's the takeaway from this? Well, if you're going to build a home theater, if you're going to build a home studio, make sure you don't make a cube. Make sure you do not make something where the height, width, the depth are nice integer multiples of each other, right? And make sure you put appropriate absorption in. So, in these trihedral corners, these are really good places to put in absorption. Rigid fiberglass absorption. You can make or buy panels from a variety of manufacturers relatively inexpensively. Put those in the corners. They will help a ton, okay? All right, so you might want to go to this URL over here and check this out. It's a fun little thing. It's nice that they put this up. There are other calculators out there. Look around, see what you can find, all right? Okay, so in the next part, what we're going to do is look at some examples of rooms, how architects have dealt with certain kinds of problems, in some cases very effectively, in some other cases where people have sort of tried to fix an existing problem, so we're going to talk about that. I think you'll enjoy it. Until then, if you have any questions, put them down in the comments, and I'll see you next time. Take care.